Good morning, good afternoon, or good evening, wherever you are in the world. Welcome to the Global Math Department. My name is Lena Taro, and I'll be your host tonight. I say tonight because it's 9 p.m. where I am in Pennsylvania. We will be hearing from Eric Milou on the status quo in high school math is unacceptable. Before I begin our session, I'm going to tell you a little bit more about the Global Math Department. The Global Math Department is an organization that's run entirely by volunteers. To keep these free, high-quality PD sessions going, we need webinar hosts, webinar speakers, and writers for our weekly newsletter. Newsletter writers share about an area of math or math teaching that resonates with them or discusses recent math blogs that help teachers reflect on their practice. If you'd like to volunteer or know someone who would be great in any of these areas, please have them email us at globalmathdepartment@gmail.com or have them reach out to us on Twitter. So we're going to get started here. I'd like to introduce our speaker. Our speaker is Eric Milou, professor of mathematics at Rowan University in Glassboro, New Jersey. He has taught at Rowan for the past 25 years and served 6 terms as the president of Rowan University Senate from 2007 to 2013. He previously served as president of the Association of Math Teachers of New Jersey and the program chairperson of the 2007 NCTM annual meeting. He is one of the authors of Invigorating High School Math with Steve Linwan, NCTM's Catalyzing Change in the Middle School and Envisions grades 6 through 8. He was the recipient of the Max Sobel Outstanding Mathematics Educator Award in 2009. And Dr. Milou earned his doctorate from Temple University in Mathematics Education, a master's in mathematics from Westchester University in Pennsylvania, and a BA in mathematics from Franklin and Marshall College, also in Pennsylvania. So people are saying in the chat they can't hear us. Okay, well, actually, I think that was hopefully a little while ago. Are there people that can hear me? I see a couple people that say they can hear me. Yeah, Chrome works a little bit better, I believe. So if you need to restart, please do that. And this is being recorded, and it will be shared about 24 hours after the presentation. So if you missed something in the beginning, you can always go back and rewatch it a little bit later on. Please feel free right now to introduce yourselves in the chat, telling us what you teach, where you teach it, and what your Twitter handle is, if you have one.
I think that's my cue, Leah, so thank you for that very nice introduction. I usually start this with asking people if they know where Rowan University is, but Leah ruined that, and she said it was in New Jersey. Yes, it is in New Jersey. It's right outside of Philadelphia, only about 15 miles outside across the river from Philadelphia. Rowan University used to be called Glassboro State College, but 28 years ago, a man by the name of Henry Rowan donated $100 million to our university. The very next day, we changed our name to Rowan University. So if you have a spare $100 million, you can have a university named after you too. We are a public state institution. We have 20,000 students, and I've been there for 25 years as a professor of mathematics. So we're going to get started right away here. If you have any questions, I kind of have the chat hidden off to the right-hand side that you can probably see. So please just jump in if you have a question or something. And thank you so much for joining me on this late night on the East Coast and wherever you are. Maybe it's a little earlier. So I want to start with my dear friend, Matt Larson. Matt Larson was NCTM president back in 2016. And Matt had the courage to say, I think for the first time, an NCTM president had the courage to say that today, it seems as nearly everybody agrees that high school mathematics sucks. Oh, sorry, wait, Matt said needs to change because Matt's politically correct as president. I am not. But he had the courage to say that. He's far too long. High school math has not worked for far too many students. High school math has not changed substantially in his lifetime. Matt's a 50-year-old man like myself, nor has it changed substantially for students, teachers, schools, districts, and states. It's clearly an issue. It's a critical issue. And I applaud Matt for doing that and saying that back in 2016. And that led to the book Catalyzing Change in 2018, which I'm going to say a little bit about in a second. But the big picture here is I argue, Matt argues, Catalyzing Change argues that mathematics pays way too much attention to preparation for calculus. In other words, algebraic symbolic manipulation. Stuff that's computers can do nowadays, stuff that Wolfram Alpha can do nowadays, stuff that Google can do nowadays, and ignores the reality of how important statistics, data analysis, and modeling have become. I mean, the pandemic has exposed this more than anything, in my opinion. You know, we have all these questions based on data during the pandemic. What do these graph trends mean? What's the impact of wearing a mask or not? Did quarantining make a difference or not? What's a double-blind study? Shouldn't every kid leaving high school know what that is? It was such an important part of the vaccine, going through a double-blind study. Where do kids learn about that? No, they're too busy factoring quadratics for 6 weeks. And it just really, really concerns me. You know, you see a lot of data out there. Do we know how to interpret the data? Do we know when the data is correct or incorrect? You know, here's data from the San Francisco Chronicle. It's from their Twitter feed not too long ago, in late 2021, from their Twitter feed. The San Francisco Chronicle says car break-ins up 753%. And I look at this graph and it just makes me want to puke. That is like the worst statistic I've ever seen. It is so misleading. Can anyone tell me real quickly why is that statistic completely misleading? Always just seeing if someone's paying attention. Why is that statistic completely misleading? Yeah, the host coordinator. Is that you, Leah? Just put that in there. You know,
that is me. That is me.
Right. Leah's never seen this before either, guys. Yeah, it's actually down from 2019. It's not up. It's only up because in 2020, COVID started, and not only were we all in our houses, the burglars were in their houses too. It's kind of funny if you think about it. Even crime went down. Crime is not up 753%. Crime is actually lower than it was pre-COVID. But yet, someone made this headline and posted it on the San Francisco Chronicle site. And it's just completely misleading. Kids need to be able to talk about that. And why is it misleading? This one's my favorite, though. This one is also at the very beginning of COVID. It's very specific. This is something called Google Trends. You can track trends on Google. What's being searched for? What's hot? What's not? On May 10th, the search for federalism barely ever existed. May 10th, 2020 again. On May 11th, it looked like the whole world searched for the word federalism. May 12th, no one searching for it. May 13th, no one ever again. Why in the world was the whole country searching for federalism on May 11th, 2020? Don't you want to know? Why? Fascinating data. Anybody answer? No one ever searched for federalism ever, except for May 11th, 2020. Why? Interesting answer by Donald. That's not correct, though. Donald says Supreme Court nominations. Not it, but very interesting, insightful guess there by Donald. Anybody else? Why is federalism searched for on May 11, 2020, like the whole world searched for it, and never ever searched for it ever again? And Kevin's good guess there, mask mandate also. But here's the real reason. I don't want to prolong this in a webinar like this. The real reason is that was the AP history test, guys. And since it was May 2020, beginning of COVID, every kid was taking it at home, and every kid cheated and Googled the federalism because federalism was on the AP history test. Just fascinating what we can find out by examining data and examining trends. Here's another one. This is how diverse is Congress. Should we not be talking about this in math classes and looking at the data? God, this data just jumps out at you. I'm not going to make any political statements here, but you can see the data and the discussions you could have between the diversity of the House of Representatives and the Senate. Just a wonderful data display. So all this really stems from what Matt started in 2016. This book came out at the end of Mac's term as president in 2018 in the spring at the NCTM annual meeting, catalyzing change in high school math. I'm not an author of this book. Two other books follow it. I am an author of the middle school book, and there's also an elementary school book. Both of those books followed this this one in 2020, but this was the original in 2018. I think there are 5 main points out of this book. Is that what's the essential content that all students should learn in high school math? What are math pathways and how do we implement them? That math modeling must permeate everything we do in high school. That we must be cautious of acceleration. And furthermore, tracking is insidious. And we have tracking in almost every high school in America. And NCTM just has made such a strong statement here. That is absolutely insidious practice. And I think Catalyzing Change has kicked off these conversations. Don't think it's gone far enough. And I think there are some mistakes and missteps in Catalyzing Change that we're going to talk about. And talk about what's next. What needs to happen. What we need to build on now that Catalyzing Change is out there. So here's, I think, the major misstep in Catalyzing Change. There's an important paragraph in the book that high schools should offer continuous 4-year math pathways. Totally agree. Every kid should take 4 years of high school math. It's not true in all states. With all students studying math each year, including 2 to 3 years of a common shared pathway. And I think this is a major mistake by NCTM. They couldn't decide should all kids take a common 2 years of math or a common 3 years of math. And NCTM basically punted. They wouldn't come out there and say, is it necessary for all kids to take a common 2 years of math or 3 years of math? In other words, what did NCTM not want to say? Anybody in the chat? What were they afraid to say here? What were they afraid to say? I don't know if the correct word is afraid, by the way, but what did they not say here when they say 2 to 3 years? Anybody? Yes. And they were afraid to say just what Lisa put there. They were afraid to make a decision on Algebra 2. 2 years of common math for all kids in high school would clearly mean all kids should take algebra and geometry. 3 years of common math would be algebra, geometry, and Algebra 2. And NCTM really did not want to take a stand there. They punted. They said 2 to 3 years, and I think that's unfortunate and a major misstep. Kathy Seeley, another former president of NCTM, was not so much afraid. As soon as the book came out, Kathy Seeley immediately pounced and said, is it time to kill Algebra 2? I did think there should not be a question mark there. I think there should be an exclamation point. Kathy said, I hope such critical conversations are occurring across the country. We believe that high school math should prepare all students after high school. Algebra 2 needs to be one of the major targets of the conversation. Kathy continues, the solution does not lie in placing students in special sections of Algebra 2 that contain little Algebra 2. Rather, the solution lies in taking a hard look at Algebra 2 with an eye towards grading something that can serve students better. I applaud Kathy for that. I applaud Kathy for taking that stand and saying all students should take Algebra 1 in geometry and non-track courses, and then that we should have math pathways after that. We should have an Algebra 2 leading to calculus pathway like we always do. And we should have a data science pathway, one of the major, most growing fields in mathematics. And we should have a quantitative reasoning pathway. We should have choices for kids in their 11th grade year and their 3rd year of high school. And that's what a future, I think, looks like. And what's exciting about this work is there are states out there doing this work. I really think Oregon leads the country in doing this work. Do I have any Oregonians on my on the webinar tonight? Any Oregonians? Am I saying that right? Oregonians? No. Because I think Oregon, Mark Freeg is supervisor there. I just think he does an amazing job with putting the 21st century math curriculum out for the state of Oregon. And look at the model here. The model is all kids take the algebra and function course. But notice in their 2nd year, they've cut geometry down, and that geometry is a half-credit course and data science is a half-credit course. And all kids are taking algebra, a geometry, and data science in their first 2 year high school. And then with 3 pathways, an advanced algebra to calculus pathway, a data science pathway, and a quantitative math pathway. I believe it's a beautiful example of the changes we need in high school mathematics. Other states, plenty of other states doing this work. Here's Ohio. You look at Ohio, very clearly it's saying that all kids need 2 years of mathematics, algebra 1 and geometry, or 2 years of integrated mathematics, which of course would be much better in my opinion. And then 5 pathways as kids reach their junior year of high school. 5, some people would say might be too many choices, especially for small high schools. You notice Oregon had 3. You see the 5 pathways in the Ohio diagram, from statistics to data science to discrete math to quantitative reasoning to algebra 2, which leads to calculus. 5 options. What's very interesting is they make it clear that all of these are algebra 2 equivalencies to all Ohio State colleges. And that's really important. I think Leah's trying to put that note in the chat, that colleges do recognize that these are alternative mathematics courses that are equivalent to Algebra 2. This is St. Paul in Minnesota, and St. Paul has developed their pathways, 2 years of integrated algebra with geometry, and then 5 pathways for kids in their junior and senior year, from statistics to finance to engineering prep. There's traditional calculus pathway they call engineering prep, to a trade pathway, to a coding pathway. So there's movement out there. There's excitement out there about reinvesting and rethinking what high school mathematics should look like, and not all kids moving from algebra 2 to pre-calculus. This all comes about with thinking about where kids are going, thinking about their post-secondary careers. If you're going into a bio, like at the bottom of the chart here, biology or engineering or math or physical science, you need a traditional pathway. But if you're moving into the arts or humanities or applied arts or natural resources or hospitality, it might be better for you to have a quantitative reasoning pathway. If you're moving into the social sciences or library or psychology, it might be better if you have a data science pathway. It's all about appropriate mathematics for appropriate post-secondary careers. Of course, Joe Bowler leads the train here, so to speak, out in California. Joe Bowler's been very, very vocal about modern high school math should be about data science, not algebra 2. If you know anything about Joe's work in California, she has clearly put together a completely free data science course. Completely free data science course out of Stanford in Joe Bowler's shop. I encourage you to look at it, download it, completely free. Amazing stuff, unique stuff. It is not just a replacement for the old-fashioned probability and statistics. Nothing even similar to that. It's fascinating stuff. All right. So people push back, and I like the pushback. People push back, but what about this? What about that? And the pushback is important. People push back about the SATs. What will happen? Well, I think the trend on the SATs is clear now. We have thousands of universities who do not require the SAT. The University of Chicago in 2018 was the first top 10 research university to stop requiring it. And I think it's a really exciting move by University of Chicago because, again, they're a top 10 research university. There are 2 things that the University of Chicago experienced in 2018, again, before the pandemic. 2 things that happened when they stopped requiring the SAT. Any guesses on what were the 2 things that happened at the University of Chicago once they stopped requiring it? And again, University of Chicago is up there with Princeton and MIT as one of the top research universities in the country. But 2 things happened. Any guesses? 2 things happened? Yep, Leo's right on the ball here. More students applying than ever. They had the greatest number of freshman applicants ever. And yes, Kevin's right on the ball on the second one. They had the most diverse freshman application pool ever. You don't think other universities are looking at that when they had a larger diversity pool than ever, and they had the largest freshman application pool than ever. And of course, the University of California, the entire system, has now said they will no longer consider SAT and ACT scores. But what about colleges? There have been some in the chat. What about colleges? We can't move. We can't make changes in high school until colleges do so. What's so interesting about that is I fundamentally believe that colleges are in front of high schools on this. While Catalyzing Change came out in 2018, the MAA, the Math Association of America, actually released a book in 2015 called A Common Vision before Catalyzing Change. And that Common Vision book in 2015 said all the things that Catalyzing Change has already said. Is that colleges need to make these changes, need to scale up pedagogical methods, need to articulate clear pathways, and remove barriers between placement and transfer students. The fundamental first page of the Common Vision, which again, a book I encourage everybody to read, was the status quo is unacceptable in collegiate mathematics. It's powerful. And of course, that's where I'm stealing the words from my talk here. From the MAA, the Math Association of America, saying the status quo is unacceptable, way before Matt Larson and NCTM has said it. Leah put on the chat, Leah stole this next slide, about a couple weeks ago when Harvard has put out some important points about what they feel is important, what Harvard feels is important for their incoming freshmen. Just call your attention to the bottom paragraph. It says specifically, calculus is neither a requirement nor a preference for admission to Harvard. We understand that many students have no intention to pursue college coursework that requires calculus, and other students are unsure of their future college studies. We also understand that not all students have the same opportunities to take certain math classes in high school. About 1/3 of American high schools don't even offer calculus. Thus, we encourage applicants to pursue the pathways through math that are available to them and aligned with their career interests. Very powerful statement at Harvard. Working with some people at Harvard, trying to design some new math courses for their incoming freshmen. I think you're going to hear a lot more about what's going on in Harvard in the next year or two. Other headlines you see across Harvard was brand new, as I mentioned earlier about Cal State and University of California system dropping intermediate algebra as a requirement. Or CUNY, the City University of New York, to revamp remedial programs. What did CUNY do? One of the largest systems in the country again. And CUNY, for those who need remedial classes, there will be new requirements. In the past, all students had to pass algebra, regardless of whether they were English, economics, or math majors. But now in CUNY, they will offer alternatives like quantitative reasoning or statistics. It doesn't make sense to prevent students from taking college-level courses because they don't have the skills that they will never use. But yet, we still sit them in Algebra 2 classes and ask them to factor for 7 more weeks for things they will never, ever use. I actually believe colleges are ahead of high schools. Hate algebra? Michigan State has good news. You don't have to take it if you're not interested in STEM careers. There are headlines like this across the country, from state to university to colleges. Of course, I understand that maybe these are still not in the majority, but there is a movement out there. There's movement we can capitalize on and have conversations with our colleagues and our colleagues in colleges. Michigan State University says we're not making college easier, we're making college more suited. Students will still have to take math, but there's no reason for a theater major to take calculus. So well said. So the bottom line of all of this is this main question right here, is why is proficiency in algebra somehow correlated to success in college for non-STEM majors? How is proficiency in factoring quadratics or completing the square or rationalizing the denominator have any correlation for success in college? Well, it doesn't. If such algebraic skills are a barrier to obtaining a degree and it's not a tool used after graduation, then why do we maintain that barrier? Because we always have, and that's unacceptable. Keith Devlin, the NPR guy, says it best. The problem with college algebra is it takes a revolutionary method developed in the 9th century and presents it as a set of decontextualized procedures. Yes, like turning the Shakespeare play into a Twitter thread of key ideas. Gosh. Tom Vander Ark, not as much of a well-known name as the math guy. Tom Vander Ark, though, very interesting. Tom Vander Ark's an engineer. He's got a master's in finance. built real estate, invested a lot of money, but hasn't factored a polynomial in 40 years. It's time to stop torturing kids by making them factor polynomials. It's time to stop using Algebra 2 as a screen that keeps low-income kids out of meaningful careers. It's time to start using computers for what they're good at, crunching big data. Let's stop asking young people to manipulate systems, to manipulate algebra that Wolfram Alpha and Google can do, and start asking them to solve real problems. World Economic Forum listed top 10 skills in 2015, and then again in 2020, problem solving, critical thinking right at the top. By the way, you know what skill number 11 was? Skill number 11 in 2020. Any guesses? I'll tell you. Skill number 11. It was factoring quadratics. Just missed the top 10. I hate saying that joke on Zoom because I can't hear if anybody laughs. So could you at least tell me if you laughed at that? So what is algebra anyway? You know, I bashed algebra for a half hour, and I always don't mean that I'm bashing algebra as this horrible thing. I still want all kids to learn Algebra 1. But I question if the repetition in Algebra 2 is something we need. You know, the first half of Algebra 2 is just a repeat of Algebra 1. Okay? Oh, thank you, Enola. I'm probably saying your name wrong, but I'm glad you laughed. So what is algebra anyway? And this slide's totally messed up here because it's giving you the answer. I didn't want you to give the answer there. I totally messed that up. I'm going to go full screen here so I don't, I just gave away the answer. So what you were supposed to do in this problem, which I gave away the answer here, is that you were supposed to put the numbers 1 through 9 in here so that every row, every column, and the diagonal sum to the same number. And that's called a magic square. You could Google and look that up, but of course, if you don't tell the kids that it's called a magic square, they wouldn't know what to Google. And then you put the numbers in here, and it's so interesting to look at the patterns and what happens with the numbers. And you got to say, well, what's his point anyway? Wasn't he talking about algebra? Yeah, I am. Hold on a second. But we put the numbers in here, and 5 goes in the middle, and all the even numbers go in the corners. So intriguing. The odd numbers go in between there. And now every row, every sum, and every column adds to 15. Fascinating. Such an interesting magic square there. Why is it 15? Why is 5 in the middle? Why is the even numbers are on the corner? But still, wasn't he talking about algebra? What's going on here? Yeah, so here's the point. That's the magic square. It's a wonderful magic square using the numbers 1 through 9 once and only once. However, it's only one magic square. It's really not that interesting after you make it, because you only made one of them. If I asked you to do a different 9 numbers, would you be able to do it? How long would it take you to do it? So far, you only made one of them. So what algebra really is, which we completely do not teach kids, is the unbelievable power to generalize something, the unbelievable power to look at the structure of something. So look at the structure of this magic square. 5's in the middle. So instead of putting 5 in the middle, since the definition of algebra is the intensive study of the last 3 letters of the alphabet, we should put X in the middle. And then we should look at that structure. What about that structure that starts at the top left to the bottom right? And I say that word structure a lot because that's really what I believe algebra is. That top left to the bottom right, don't you see a 6, 5, 4, which is 1 more and 1 less than X? And then what about the other diagonal? What do you see now that you probably didn't see before until you made the transition to looking at the algebra? And the other diagonal, you see 3 more and 3 less. And now it starts to uncover itself. Look at the missing column, 4 more, 4 less. Look at the missing row, 2 more, 2 less. Wow. Do you see the power of algebra? That algebra enabled me now to look at this magic square, make some generalizations, and now I can make a new magic square in a matter of just seconds, giving any value for X. Good question would be, what's the sum of every row, every column, and both diagonals, by the way? And of course, a quick algebra would say that the sum of every row, every column, and both diagonals is 3X. 3 times 5 is 15, as in the top one. That's the beauty and the power of algebra. That's how people use algebra in the real world, to look at structure, to look at the models. But further all, I'm not satisfied with this example yet. Because I kind of look at it and I ask myself more questions. I ask myself again, looking at that 6, 5, 4 diagonal, which is now x plus 1, x minus 1. I ask myself, do you really have to add 1 and subtract 1? Could you add 7, subtract 7? Could you add pi and subtract pi? Why is it 1 there? So, of course, let's make it not 1. Let's make it a new variable. Let's make it z. But if we're going to add z on the top left, we better subtract it on the bottom right. And I've done this lesson so many times in high school, and the next step is so intriguing. What other patterns and structures do you see? What about the other diagonal? The other diagonal has a 3 in it. Is that 3 related to the 1? So should that top right be 3z? Should that be z plus 2? Is there any relationship between the 3 and the 1? It's such a deep question, by the way. But actually, there is no relationship between the 3 and the 1. They're just completely random in some sense. They're just 1 and 3. However, there is a relationship between the 1, the 3, and the 4, meaning the 1 and the 3 in the top row and the 4 in the top row. And I think you see it now. And on the top row, you now added z and added y, so you're going to need to subtract them. And the rest falls into place. And now you have a magic square. Now you can generate every magic square in the world, given any numbers, x, y, and z. And you've used the amazing power of algebra to show structure. The beauty of algebra, the reason I think we teach algebra. However, what do our classrooms look like? Oh my gosh. Kids doing decontextualized procedures after procedures like it's 1950. And that is just a shame to me. It hurts me to see that continue like it does, like there have been no technological advances in the last 50 years. We can do better. And the flip side of this, and we talk about this a lot, is not only does curriculum have to change, and my first half of this was all about curriculum. First half about this was about pathways, and a little bit about how we can, when we still need to teach algebra, is that we can do it better. But the second half of this has to be about pedagogy. I have this point on my slide right here. It says, we ruin the surprise because we just tell kids. But people say we want to do more inquiry learning, and I agree. But that inquiry learning has kind of got like a lot of bad press that like somehow kids are going to discover everything. And I like to think about that a little bit differently. And I like to just show you an example of how I think we ruin the surprise. So I'm going to move out over here. I think you can still see my screen. And I'm going to go over here. And I think, again, kids don't have to discover everything, but they shouldn't be told everything. Like in this example, I'm going to say, hey, anybody remember what a root is? If I'm in a pre-calculus or an algebra 2 class, everybody says no. And I say, I'm not going to have a slide with the definition for you to copy it down. That's ridiculous. What I'll just show you real quickly is that's a root. They're 2 blue. And this is not a root. Now you turn to your partner and you write down what a root is. I firmly believe that's 21st century math teaching, not copying notes or PowerPoint slides. It's an engagement of there's a root and there's not a root. Now you discuss and then share out to me your definition of a root. That's engagement. What do you see? What do you don't see? Let's discuss it. Let's come to an understanding, even though you were supposed to learn this 2 years ago. So now you have some idea what a root is. You have some idea what a root is, hopefully. Let's explore it even more. So in the chat, you're going to have to put one of 3 words. Only one of these 3 words. Must, not, or might. Let me explain that better. There's a big circle covering up certain parts of this function. So I'm going to move A in a second. I'm going to move A away. And in the chat, you're going to put must if you think there must be a root under A. You're going to put not if you think there must not be a root under A. And you're going to put might if you think there might be a root under A. All right, you got 10 seconds. Must, not, or might. Who's still paying attention? Got a couple mites. Got a couple mites. I got 3 mites. Oh, come on. There's more than 3 out there. 4, 5. Yeah, you're all wimpies with those mites. Oh, such a wimpy crowd tonight. All right, let me give you a hint, though. How about if I do this? How about if I do this? Would your answer change right now? Your answer change right now? Would your answer change right now? I don't see any answers changing. Any answers change now? I moved A a little bit, and now I think I get some different answers. What's your answer now? I moved A. Is it still might? Yes, you can see the x-axis, so it's no longer might. You're all going to say not now. Good. All right, I'm going to skip B. No, let me not skip B. Oh, the chat has a slight lag. Thanks, Rachel. It's a little slow there. Thanks, Rachel. What about B? What about B? Must, not, or might? B. You should probably put the letter in front of your word, so I know you're talking about B. So you might put B must, B not, or B might. Okay. So I got a lot of must, of course. B must be a root. Yes, you're all correct. And now what about C? Okay. C, is it must, not, or might? What about C? Is it must, not, or might? So, of course, C, obviously, C. Yeah, I see that lag in the chat now because I'm still getting some B's. So, C is obviously not. And we have this deep discussion about this understanding of a root, and we go through several more examples. I'm just going to jump to this last example right now. Okay, let's go quickly. A, I'm going to help you. A, must, not, or might. I'll do a shout out to Michael Goldenberg. Just your work is unbelievable, amazing. I've followed you for years, Michael. I'm just honored you're here, and amazing work you've done out there. So A is definitely a not. Okay, what about B? What about B? I'm helping you again here. What about B? What about B now? So I got a lot of knots on B, and of course I didn't move A. I never moved A. A and B are definitely knots. And finally C. Finally C. What about C? And of course we have all these musts on C. And a couple more people get in there. And of course you're all wrong. C does not have a root. And look, if we were in a class right now, there would be just a huge aha moment there. There'd just be a huge moment. Now, some of you, because you're math teachers, were all anticipating that in the chat. Some of you were just couldn't hold back. You just had to put that in the chat like Rachel, only if it's continuous. But that's the whole point here, is that we've ruined that surprise. That surprise when you move C, and every single kid expected it to be a root there, and there's not. You have that reaction that Tatiana put in the chat. You have that reaction, oh my gosh, what did we just learn? You assumed something, and that assumption was incorrect. And we just learned something so powerful about continuity. It wasn't given in a definition. You didn't discover it. It was done in a way that you participated. You expected something to happen, and it didn't. I can't tell you enough how I think that's how learning occurs. Learning occurs actually, oh, this is definitely going to happen. I know it's correct. Oh, it's not correct because I made an incorrect assumption. Just unbelievably powerful. If you want to do that in your own classroom here, the link is in the PowerPoint. I'll give you this PowerPoint at the end. I encourage you to try it with your kids. It's an unbelievable, powerful moment. So let me continue for the last 15 minutes here or so. As a professor, it's law. It is a law that I must show Bloom's taxonomy in every presentation. You know, it's a law. When you become a professor, they tell you you have to have Bloom's taxonomy in every presentation. So I just stick this in here. But maybe not. Maybe there's a reason for this. And and again, I think the pandemic has exposed this, is that we still spend way too much time down at the bottom of Bloom's taxonomy, especially in algebra class. And kids just go home and they do everything on Wolfram Alpha, they do everything on Google, they do everything on Photomath, and they do everything on Chegg. And they use all those resources, and you tell them they're cheating. And I say, you're not cheating. I gave you stupid problems that you could Google. And maybe we shouldn't give them stupid problems that they could Google or use things like Photomath. Maybe we should finally think that we need to move the questions we ask kids to the top of Bloom's taxonomy. And I think that's so important. And Robert Kapinski's work, I think, is the best at this. Robert Kapinski's written a book called Open Middle. And it talks about this very, very simply. And I look at it like this. The first problem on the screen, solve 3x plus 5 equals 11. Photomath does in 2 seconds. It's a worthless problem in the year 2022. The second problem is beautiful. Photomath can't solve it. Only the human brain can solve it because it uses a different verb. It doesn't use a verb like solve that Photomath can do. It uses a verb like create. Create a 2-step equation with solutions to x equals 2. Oh my God, if you ask kids that, you get an amazing amount of different answers. Some answers you might not even like 2x plus 0 equals 4. Then you have this big debate, is that a 2-step equation or not? And you'll get so many different answers, so much creativity and understanding of what it means to have a solution x equals 2. Robert's book is amazing at this, talking about what the vogue word now is DOK, or death of knowledge. You know, that's what everybody's talking about. Robert calls it slightly different in Open Middle, but death of knowledge. From death of knowledge 1, which Photomath and all technology can do, to death of knowledge 2, to death of knowledge 3. Look at the examples of death of knowledge 2 and death of knowledge 3. Death of knowledge 2, you have to create 2 equations using the digits 1 through 9, where x is a positive value and 1 where x is a negative value. You look at the 2 answers there. And what can you discuss? What do you know? How do you realize that those answers are correct? Well, the coefficient of x is positive. As long as the coefficient of x is positive, it's irrelevant with respect to the sign of the answer. But since the 2 is less than the 3, you have a positive answer. Since the 6 is more than the 5, you have a negative answer. And then you look at DOK3, and some people ask me a lot of times, well, why is that a higher depth of knowledge? Why is that a higher depth of knowledge? The third example here, because it says to create an equation this time that has the greatest possible solution. And I have an answer on the board there, which I probably should have covered up. I have an answer 1x plus 2 equals 9, and I claim that's the greatest. I claim that's the greatest you can make using the digits 1 through 9 only. But could you possibly get greater? Are you 100% sure that's the greatest answer? Could you get greater? I've had kids beat that. Of course, they kind of use these slightly different ideas. They use things like 1/2 x, or they use things like 1x plus 2 equals 98. And maybe that's kind of not using the definition of the word digit, but I think it's unbelievable, beautiful mathematics. There's a lot of great work out there on problems like this that raise the DOK level, that avoid the technological quote unquote cheating. Here's another beautiful example, is enter different numbers so all the areas are equal. I picked 24 here. You might wonder why I picked 24. Why would I pick 24 as the areas? Well, because 24 has a lot of factors. It's kind of implied on here. Well, maybe it's not implied that you're supposed to just use single digit numbers, but I've never been able to do it with just single digit numbers. But it's a wonderful problem again that Photomath cannot do. Here's a calculus one, which I did not put the answer in. So you got 2 minutes, my calculus teachers out there. Use the digits 1 through 9 to fill in the boxes to create a true statement, instead of plugging and making kids do 20 power rule problems. you just give them this one problem and say, how many can you come up with? By the way, I've had kids come up with 12 different answers here. And you really have to deeply understand the power rule. You have to understand what's going on with those exponents. What would be a good fraction to put in front of the variable? Where would be a good place to put the number 1? Anybody think about that? And we increase our way up Bloom's taxonomy, more important today, more important than ever before today, because of the technological tools that kids have available to them. I'm kind of stalling to see if anybody would give me an answer here. But it's a tough one. I don't know how many calculus teachers I have out there, or how many people remember their calculus. Oh, let's see. I got one on there. 8, 6, x to the third. So that's 24 over 6. That's 4 over 1 x to the second. That certainly works. She did not repeat any digits. She used the 8, the 6, the 3, the 4. It's 4 over 1. And the 2. That certainly looks like a good answer. There are at least 11 others. And I just want to point out one other person's work. Robert Kapinski, very popular. His book, Open Middle, very, very popular. I'm going to give a shout out to another teacher. This is a teacher up in Canada. His name is Nate Banting. I think Nate Banting's work is out of this world. He doesn't have a book. Nate Banting, just look at the beauty of this problem. There's 10 conditions. You could write 10 linear equations, one for each of the 10 conditions. But which conditions could you combine together so that you could write less than 10 equations to satisfy all 10 conditions? Could you pair them up and write 5 equations that would satisfy the 10 conditions? Could you do it in just 3 equations that would satisfy the 10 conditions? Just an amazing deep problem that, again, no technological app can do, but it certainly could support you in doing. In fact, that might be the way I started. I might look at the first condition like positive slope, and then the second negative x-intercept, and I might think about using a Desmos to graph an equation that has a positive slope and a negative x-intercept. Could I also get that one to go through 2, -3? I'm not sure. But I certainly couldn't use the fourth condition because I couldn't have a line with a positive slope and a negative slope, which conditions paired together nicely. I call this my name that tune problem, because what's the least amount of conditions you can do this in? Or what's the least amount of equations you can do this in? I encourage you to look up Nate Banting's stuff. He calls it menu math. Amazing stuff. The link's on the bottom of the slide here. There's the answer. Nate tweets often, and I just want to show you one of his tweets to show you, I think, what just the beauty of the kind of things he asks his kids to do. He says, build an argument. It's 10th grade math time. Build an argument so convincing that it crushes your nemesis. Just look at the first one. Any linear function with a positive slope will enter the first quadrant. True? Always? You better build me a very convincing argument. Any linear function with a positive slope will enter the first quadrant. Wow. Powerful. Always true? Sometimes true? Never true? How would you build a convincing argument? Every linear function goes through at least 3 quadrants. Always true? Sometimes true? Build me a convincing argument. So intriguing stuff. So let me end here. Just want to end. I always like to end with a little game here. So I'm going to play a little game with you, and I'm going to give away a prize to the winner. So this game is called The Lowest Number Wins. So I'm going to give you a code, and we are going to play The Lowest Number Wins. So I'm going to put it in the chat, and it's in the chat. If you guys want to click on it and play the game with me. How you play the game, I do have a prize for the winner. Okay. How you play the game is the winner is the person who writes down the lowest counting number. When I play as high school students, by the way, I have to remind them like 100 times what a counting number is. Counting numbers, not 0, not fractions, not decimals, just 1, 2, 3, etc., 4, 5, 6. And the winner is the person who writes down the lowest one. Well, why wouldn't you write down 1? Oh, there's a catch. You only win if you're the only person who writes down that number. So if 5 people write down 1, you all lose. You have to be the only person to write down the lowest number. For example, if 10 people play and they write the numbers 1, 1, 2, 2, 2, 3, 4, 4, 5, 6, then the person who wrote the 3 is winner, because 3 is the lowest number that only one person wrote. So are you ready? We're going to do a quick round here, and I'm going to send out a prize to the winner. So I'm going to put you on screen number 2, and you have 10 seconds to type in your number. Ready, go. Five more seconds. 4, 3, 2, 1. And I'm going to pause you, and we will look at it. And whoops, I hit the wrong thing there. And the winner is number 4 by Lisa. Lisa is the winner. Nice job, Lisa. I'm going to show you something weird that happened there. If someone in this room, someone on this webinar would have picked 1, you would have won. No one picked a 1. Fascinating, is it not? Okay. No one picked 1. I've done this hundreds and hundreds of times, guys. 1 wins 90-some% of the time. Such a psychological experiment with mathematics. All of you guys did not pick 1. If just one of you would have picked it, it would have won. Lisa won with 4. No one picked 1. No one picked 2. No one picked 3. Such an intriguing, interesting math game. Lisa, I'm going to put my, Michael was frozen. Lisa, I'm going to put my email in the chat. If you email me and send me your address, I'll send you out a little prize. All right. So let me end with just a couple last slides here. And I consider this an unbelievable opportunity. An unbelievable opportunity to design, plan, and think differently about math, secondary math. To build something that serves the needs of our students, listening to what they need and what they say. Let's use the lessons we all learned during the pandemic and start for planning a new vision. One where high school math curriculum and assessment truly inspires and makes a difference to all students. I have 2 links here where you can read some more at. First of all, I'm going to put the link in the chat of this PowerPoint. So the first link in the chat is the PowerPoint link. And the second link in the chat is just resources. I put together about 100 links on one spreadsheet, about 100 resources. Resources for curricular resources, instructional resources, and research. So there's 2 links I just put in the chat. The first link, again, is to download this PowerPoint. And the second link, looks like I have a little footnote in front of there. It looks like a little A in front of there. It looks weird. I'm going to put that second link again. No, that A keeps coming up. Okay. Here's a second link without the A. Those links don't look like they're clickable, but hopefully you can copy and paste them. Someone give me a thumbs up.
They're actually clickable. They do work.
Okay, they do work. Thank you so much. So again, the first link in there is to download the PowerPoint. The second link in there is a spreadsheet I put together of resources, curricular resources, instructional resources, and research. It's really an honor to speak to so many people tonight and to be part of this global math department. I'm gonna give you my email, leave this up on the screen, my email, my Twitter, and unless I have a couple minutes left still, if anybody wants to throw out any questions. But again, thank you so much.
Yep, I don't think I saw any questions in the chat. Of course, I now have to find my chat because I was doing the Desmos activity and playing along with that. But if you have any questions for Eric, please feel free to post them in the chat right now. And while I'm waiting for any of those questions to come in, I'd like to let everybody know that our last session of the 2021-2022 school year is on June 28th. So that's 2 weeks from today. The session is called Data Rich with Diagnostics with Kat Hendry. She will be our speaker for that session. And that's in 2 weeks. So I hope to see some of you there. Let's see if there's any questions in the chat. I do not see any. So thank you very much for sharing with us tonight. I think I feel like some of the things over here are familiar. So maybe I saw you give a similar talk at an NCTM presentation. But these are great ideas, and hearing about them again makes me really want to push the colleagues that I have in my department to not really worry about factoring trinomials for the business math class. All right. Thank you, everyone. Have a lovely evening.